Right, thank you very much. So this is going to be a very, very short talk about a new way, or a semi-new way of designing syscalls such that you can extend them sanely. And it's based on some work that was done quite a few years ago by some other folks, but has sort of been reborn given some new syscalls that recently came in to the kernel. So first of all, I guess the first question is, why do you want extensibility, or what are sort of the spectrum of extensibility you can imagine? And I've sort of given a couple of examples of syscalls that have different levels of extensibility. ioctl being the most obvious, most extensible syscall, in that it's basically a multiplexer. It's like each individual ioctl is kind of like a syscall unto its own, with different subsystems being able to set it up. And I think it's fair to say that we shouldn't make all syscalls like ioctl, I think is a fair statement to make. But then on the other end, you have things like creat, which in case you've never used creat, it's like open ocreat, but it takes no other flags. So it's literally a syscall that is all it's doing is open ocreat, o-exclusive, which is lovely. So for creat, if we wanted to add a new flag to creat, it wouldn't be possible. So we have to decide at which point where we'll be happy with for a particular syscall. And obviously open has flags, statx has an actual structure, so there's different ways you can do it. The main reason why we would like extensible syscalls at all, why isn't every syscall like creat, is because having extensible syscalls allows us to have more flexible user space code. So in other words, if you have a library that uses a particular syscall, it can make use of newer kernel features. So you have a library that, for instance, exposes some feature like openat2, which I'll get to in a second. A user of that library can use the new features without the library being modified, at least assuming the library has the right interface and all the rest of it. And applications, similarly, this is a little bit more of a stretch, but you can imagine like CLI applications or some graphical applications allowing you to use new kernel features that are exposed through these extensible syscalls without having to modify the program itself. These are things that is non-trivial if you have to create a new syscall every single time, because if you have a new syscall, you have to rewrite the program to be able to use the new syscall. So having syscalls where it's one syscall number, but you can extend it over time, is very beneficial in this respect. And ideally, we would want syscalls to both be forward and backward compatible, meaning that if you have a program obviously, backward compatibility is a requirement of any Syscall ABI, but forward compatibility would be if you have a program that's written for a newer kernel, so it has new headers and it was built on a newer system, but isn't using any of the new features. Ideally, you would like it to work on old kernels. And this is why having different syscall numbers is not ideal, is because, well, if a program is written to use a newer syscall but doesn't use the new features, when you go back to the old, onto an old kernel, it just won't work. So the oldest and most well-known way of doing extensibility is obviously Bitflags, which everyone here presumably has at least seen. And it works great. Bitflags are awesome for solving the problem of we want to add new Boolean flags to a particular syscall. The problem is that that's sort of the only place they're good for. If you want to add new arguments, or if you want to add anything like that, it's basically it's non-trivial to add them idiomatically, right? I've given otemp file here as an example, which is a combination both of open's weirdness and also the problems with Bitflags, which is that open actually takes 4 arguments, but it has historically only taken 3. And long story short, glibc had a bug a while ago, which was that when otemp file support was added, because glibc didn't know that otemp file requires the mode to be set, it would just pass garbage to the kernel, which would be fun. So that was eventually fixed, but it's an example where you've added a flag, and now an argument that was previously unused, or a register that was previously unused, now is used for something. These older programs, a program that was using glibc, couldn't use otemp file until it was fixed in glibc. So this is far from ideal in terms of extensibility. And while Bitflags are the most obvious and straightforward way to do extensions, there are some newer syscalls that don't even use them. I mean, renameat and renameat2 is sort of is a classic example of this. Is a very funny example, I guess, which is that renameat2 was just, obviously there was an extension to all of the VFS syscalls a while ago to add a directory file descriptor argument, but they forgot to add a flag argument to rename at, which eventually meant that when they wanted to have, like, for instance, atomic exchange renames and things like this, they had to add rename at too in order to work around this problem. And there are actually a couple other examples of syscalls that still don't have a flags argument, but probably will eventually have a version 2 added which have a flags argument. I've given readlink at here as an example, in that, yeah, readlink at doesn't take a flags argument, which sucks if you're like me and you want to add a feature readlink at that you need to add a new syscall entirely just because there wasn't, we didn't add any extensibility to them. The second most common way, or at least a way that is a little bit newer but still pretty old, is fixed size structures. So this is the most obvious, I mean, it's sort of, I guess, the simplest way to say, well, we need to have arguments, but we can't have 20 arguments to a syscall, so let's make a structure that just has the arguments we want. It's very simple to add new fields, assuming you've allocated enough extra space in your structure to be able to do this. You just, rename one of the reserved fields. The main problem with these is that, and I've given ShemCTL as an example. StatX, I think, is a better example, but it's StatX is like getting data, so never mind. But it's simple to add new fields to things like this. The downside is that you have to be able to know the future, right? You have to know how many extensions are going to be needed, and there are a couple of examples of syscalls that had a fixed size struct that wasn't big enough, or it's a fixed size struct where, like, the last 3 bytes are not used because there's no uint type that is useful to be fit in 3 bytes. So this is quite frustrating. And as with Bitflags, you could, in principle, add further extensions to a fixed size struct. So you could, if one of the bits in the struct is a flags argument, you could make it like, oh, here's a flag saying the struct is this size. The downside of that is that, again, it's annoying to use. With Bitflags, it would be like, oh, and the next argument is a struct, and then you would have another struct argument. But these are not the nicest way of solving this problem. Yeah, so then we come into what I'm going to be talking about now, which is extensible structs. So this is, as I said, better than sliced bread. This is a way for us to avoid most of the problems with fixed size structs without making the rules overly complicated. And so I've given openat2, which is a syscall I worked on, which will be hopefully will be in 5.6. Which effectively what it does is that you pass, so in DFD, construct path is just like open. Then you have a structure called openHow, which it has some fields in it, which I'll show you in a second. And then user space passes the size that it thinks this structure is, or rather the size of this structure in user space. And there are a couple of rules for how you handle this size, but the net result is that we can add new fields as much as we like. You can add new fields to the kernel struct, and because the user space passes both the struct and the struct size, the kernel knows which fields user space is aware of. So you remove the whole passing garbage problem, and you get, which I'll get to in a second, you get some nice forwards and backwards compatibility. But more importantly, and this is the neatest thing about it, is that user space doesn't need to care at all about what new fields have been added that it doesn't know about. From its perspective, it's just using whatever structure it had at the time when it was compiled, and nobody else cares. And this design is not new. It's actually used by 5 syscalls. It's used by Shed, SetAdder, perfevent open, BPF, clone3, and openat2 are the main syscalls that this is used for. The main reason why I decided to give this talk is because during the discussion of clone3 and openat2, there was a lot of disagreements about this style until eventually it was pointed out that this style already existed and all the nice benefits. So hopefully we can eliminate those confusions. So what are the rules? How does this work? It's a bit long, I'm afraid, but effectively the idea is that given a structure, we guarantee that, or the kernel, as the kernel community, we all agree that extension fields will always be appended to the structure. That any future fields we add to the end of the structure must have the requirement that their 0 value means the old behavior, whatever that means for a particular syscall. So the most obvious example would be a flags field. A flags field that is equal to 0 means don't use any of the new features. So you can't depend on the size of the user space struct or whether or not that field exists to determine whether or not a feature should be used. It should always be, if it's non-zero, then we use it for whatever its use is. And there's only 3 basically cases you have to care about. so k size and u size, k size is the size of the struct in the kernel, u size is the size of the struct in user space. If k size is u size, then we just copy the struct as is, pretty easy. If the kernel struct is bigger than the user space struct, that means that the kernel is newer than user space, meaning it has more fields, then we copy the user space struct, and then the trailing bytes that the user space didn't know about, we zero fill. And that means effectively because we say, well, if the user space didn't know about the new features, then they're not using them, so we can just disable them all. And that's sort of, I guess, fairly obvious. The inverse, though, when the kernel is older than user space, is where we get the nice forward compatibility feature we'd like, which is that if k size is smaller than u size, we copy the size of the kernel struct, so we ignore all of the trailing stuff from user space. We don't copy it, rather. And then we check whether or not the trailing parts are all zeroed, meaning any future extension which this kernel doesn't know about, if the feature is not used, we don't care, and we just continue on. But if there is a feature used, then we give an error to make sure that we don't accidentally ignore garbage passed to the kernel. And all this stuff is already implemented in copy struct from user, which was merged in a few releases ago. And I've ported most of the syscalls that use this style to using copy struct from user. So if you're implementing a syscall that wants to have some sort of extensibility, just use copy struct from user and you don't have to worry about it. But I think it's neat to think about, like, with these 3 small rules, we now can say, OK, any user space program has these nice extensibility benefits. So here's an example of OpenAT2, Clone 3, and BPF are both fairly similar in how they use this, which is, you have your syscall, which takes a struct in the size, and then you have some fields that you've added, and then you add future fields at the end. And so if we add a future field, let's imagine we added some field that does some other flag bits, the kernel would know that it would be 0 if it's on an old kernel, or if it's on a new kernel, you can use the new flag bits. Confusingly, this is sort of where I hope we've made some improvement over the old way of doing it. So as I mentioned, shed set added and perf event open existed before we did this for Clone 3 and so on. And these were introduced, I think, in 2014. It's a bit stranger and a bit weirder, and so I just wanted to give an example of hopefully we've improved some of the ergonomics of these APIs. Like, for instance, shed set addr confusingly has a flags field that is separate from the structure, but the flags field is unused. And the argument if you look at the commit message and everything, the argument is that this flags field can be used to change the structure, but because and the other thing is the size is embedded in the structure. So if you read the code, you have to actually get the size first. And the argument for all of this is that because the size is part of the structure, if there's an error, in other words, if you're trying to use a new feature and the kernel doesn't support it, then you would get the size of the kernel structure returned in the structure you passed. So size gets updated if you get E2 big, which is the error we give. The problem with this is basically that, well, it's not a problem, it's just odd. Like, it's a bit weird, and the whole having an extra flags argument that isn't used for anything and really should have just been inside the structure is also a bit odd. Shed get addr is even weirder because it has a size both as an argument and in the structure. So yeah, I think hopefully we've improved a little bit on that interface with just give us the structure and the size and don't worry about it. A bit of future work that I would hope we can get done, which I think will be quite neat, is right now checking what flags are supported by a particular syscall absolutely sucks. Like, you have to go and try each individual flag, and you have to, if it's a syscall that does like something potentially destructive, you now have to come up with like examples where the syscall is either a no-op or it gives you an error, but not enval, because enval you couldn't figure out whether it was the flag was missing or not. So you have to come up with, user space has to come up with a bunch of different examples on startup to check what syscalls are supported by the kernel and which features of which syscalls are supported. And it's all a massive pain. You have to do a bunch of retries. You have to come up with these flag combinations that will fail but not give you enval, which is funny, obviously, because a lot of syscalls give you enval for things that aren't invalid flags. Like mount gives you enval all the time. And then whether or not a particular field is supported at all is even more fun. For fixed size structs, you have to do it field by field. Luckily, with the extensible structs, you can do it with a binary search on E2 big, but still, it's still not great fun. So the solution to this is let's add a flag that just On return, so you set a flag inside the flags thing saying, okay, check fields is what I've called it here, but we can call it whatever, where we say, okay, here's a flag saying, this syscall is a no-op. I want you to tell me which parts of the structure that I've given you support. Meaning that if you have flags that are unsupported, sorry, you basically set all the flag bits to here are the flags that are supported for this kernel, and also any other fields you set to like all OXFF saying like this field is valid for this kernel. And then obviously you don't want it to be a no-op where you return 0, because that would be very confusing, especially with like open. You don't want to accidentally return 0 when, because that's actually an FD. So instead we can return, I've given ano as an example, which as an aside is a syscall that, as far as I can tell, has like 5 uses within Linux. And one of them I've been told is actually a typo. But yeah, basically it's ano, it's least used ano value. We can add a new one, I don't really care. Please add a new one. OK, I will add a new one. no-op or something. And ideally, this check fields flag would be the same flag bit for everything, just to avoid the ocloexec problem, where we have 15 different ways to represent ocloexec for different syscalls. And luckily, as far as I'm aware, most old syscalls that got a new version switched from U32 to U64. So actually, the topmost bit is actually free, as far as I'm aware, for most syscalls. And the rules for this would be very similar to copy struct from user, except obviously rather than reading from user space, we're writing to user space. So you would do, if the kernel size is bigger than usize, then you only deal with the first usize bytes. You don't care about anything else. So in other words, if the kernel is newer, you just ignore the bits that the kernel has that the user space doesn't know about. And vice versa, you would zero fill the parts the kernel doesn't know about, because the kernel doesn't support them. OK, and this would be like a trivial example. Obviously, because some of these syscalls don't support, this feature would not exist. You would have to deal with both. But basically, you would have the old way of doing it, find all supported bits. And then if we have check fields, then you can do something like, OK, give us open at 2 with the check fields flag. And then if you get ano or whatever new error we decide, then we can just check, does that flag contain this bit? And if it's a field we're checking for, we check, is that field non-zero? Which I think it's much nicer, and it allows us to avoid having to just retry with a bunch of examples. I mean, if you want to check if a certain open flag or rename flag is supported, you have to come up with examples where you won't break the system in checking. I guess umount is the most fun one. Like how do you check umount without doing anything bad? But anyway. Yeah, there are a couple of caveats that I just want to mention before I finish up. And this is an argument that has raged on the mailing list a little bit, is what things should be this extensible? I think it's quite fair to say that not all syscalls need to be this extensible, because well, there are a couple of problems with having to require a structure that you pass a pointer to. Namely, in some languages, I know that there's some Zig folks that complain about this, that having to allocate on the stack for a structure when it's like you're just passing one field is annoying to them. I think that, sorry? Yeah. Yeah, so I think that it's fair to say that we shouldn't have all syscalls work this way, but syscalls which are going to be extensible are going to be extended a lot. Like clone 3 is the most obvious example. Clone 3 broke past the 6 argument limit almost immediately the second after it was merged. So I think it's fair to say that some syscalls do deserve this, others maybe not. And there has been some arguments about whether ioctls should be this extensible. I think it's been agreed that they shouldn't be, though it turns out actually that seccomp already does this. There's a seccomp notify, which is extensible. It's extensible in a different way to the way I've described, but I think that the reason why it was done that way is because the way that I just described wasn't really well known at the time. And even though we can just extend stuff, the struct layout and planning from the outset is very important. Otherwise, you'll end up with a bunch of padding holes, and also you have to worry about obviously alignment of U64. Basically, all the problems we had to worry about before when it comes to planning ahead still exist. So you can't just just say YOLO and just throw everything in. But at the very least, we're no longer bound by the size of the struct is the thing we decided 15 years ago, and we haven't thought about it since. OK, that's it for me. Any questions? Oh boy.
So it looks like you're proposing that we just have arbitrarily flexible system call arguments at all times, and you'll never know at any given time what you're expected to send to your system calls. How am I supposed to deal with this from a security side, where I have no idea what information is coming in to the system call or what to expect to go out of it, because the parameters are always going to be different on
Is this a
any given
SecComp question?
Well, the question, okay, I'm getting out my pitchfork here.
Yes.
I was invited, it says right there.
Yeah.
Okay.
I regret that immediately, yeah.
Okay, so how am I supposed to deal with the fact in the kernel proper that I have no idea what's coming in on any given system call?
Well, so the struct would only ever be appended to, so you do know for a particular kernel what's being passed down, and all of the parts that the kernel doesn't know about are just being checked for whether or not they're zero, effectively. So like the meaning depends on the kernel.
Well, no, the user space is going to be, if the user space is going to be independent of the kernel,
Yeah.
and you never know what arguments the kernel is going to accept, and you're going to be passing down who knows what, because your user space is expecting to be able to do things the way they're done at this point, as opposed to things they were done 3 weeks ago. You're never going to be able to verify. How are you going to be able to verify that you're getting the right parameter? Yeah. Are you expecting that? I'll ask a question. Are you expecting the kernel to verify that the parameters you're sending are consistent with its expectations?
Yeah, so it would be basically the kernel should, I'm not sure if I'm really understanding, so the structure is going to only be appended to, so any kernel release would only add new fields, and those new fields would be...
Yeah. What if the application sends in stuff beyond what you expect?
So like more fields than you would expect.
Right. Should that be a failure?
Yeah, you would get a failure. You get E too big in that case. So you would get you would get that because you would because the value of the fields being provided is non-zero. So if someone passed a pointer or some flag that you don't know about, you get E too big immediately. Like the check is copy struct from user. Like the check is immediately after the copy from user. Like it's the next line literally in the function. So it's like it basically does like it does check zeroed user. So it's like a memture inverse of 0 bytes on the thing that's passed down.
But what if 0 bytes is a valid value?
Yeah, so 0 bytes are fine, but 0 bytes, as I mentioned, oh boy, let's see if I have it here. Yeah, so the extension fields are always appended. And any future field that we add has 0 mean whatever it was before we added the field. So this is syscall dependent, obviously. But the most obvious example is like a flags field you'd add. If the flags field is 0, then none of the new flags are enabled. And the old kernels would check, these new fields that I have no idea about, are they all zeroed? Like, are all the bytes from case size to U size, are they all zeroed? If not, then we give an error immediately. And if they're all zeroed, then we're like, okay, I guess whatever new kernel features this user space is expecting, it doesn't need. So we just continue on.
Okay.
Okay. We can continue this chat outside if you like.
Yeah.
Okay.
Hello. In ideal world where you can break backward compatibility, what would be a better way to implement that than just padding the memory with zeros? Thank you.
In an ideal world, yeah. I mean, in an ideal world, we could just make it so that we have a new struct each time we add a new feature. The nice thing about doing it this way is that so there are some syscalls that use version numbers, like the capability ones use version numbers, but the downside of having a version number which is just a version number is that old kernels have no idea what to do with it. And I think it's neat that we can try to solve this problem that way. But ideally, you could say ideally if we didn't care about backwards compatibility, then you could just make a new struct each time. Though I personally think that that being able to extend it is like a neat thing to be able to do anyway. Especially because you get forwards compatibility as well, I think is the neat thing. Yeah.
So like we've been doing this for years with ioctls in graphics subsystem, But one thing we've also added was like, you have to let user space know that this can be used. So like, we add the new fields. When user space start, you don't want the user space suddenly assuming that on older kernels it can start passing those new fields down if it's built against new headers.
Right.
So there had to be some way for the system to notify user space that it was allowed to use that. You could just keep bouncing eno sys and eno no, but it's really not. It's a bit of a hostile thing for user space to have to call a syscall 5 times if you start scaling this out. Like if I'm on an old kernel and I have to call this syscall 5 times, I have no idea which version I should be using. There should be some way for the kernel as well, possibly separate to this through some other mechanism, that it can tell user space what version of the syscall is acceptable to it or what size.
Yeah, and actually that is exactly what check fields would allow you to do. It's not as direct as here is the size. Instead, it does a little bit more where it also tells you what the flags that supported are. Yeah, sorry, he wanted to.
Doesn't that just bounce that back to user space saying it's screwed, or you call it through this?
So this is user space would do this as like the initial thing. So it's just one syscall and you say, yeah, right now this doesn't exist. So right now you're quite right. You have to do it 5 times and it's a real pain, especially if you're like trying to do it with mount and unmount. And it's like, wait a second, like, how do I not accidentally break / when I'm checking unmount? Like, exactly, I completely agree. And I think that this would be a neat thing. And the nice thing about this is that it perfectly fits in with having the extensible struct, because it also tells you the size, because you know that the last non-zero byte of the thing you get back is going to be the size of the kernel struct. Yeah. OK, I think that's it, yeah.
Well, I think we're out of time. So please thank Aleksa for his talk.